At this point, I'm going to introduce you to the first model for our game theory class. This is called the normal form, and I'm going to show you the normal form of the prisoner's dilemma game. Now, this is probably the most famous game in game theory, and what's interesting is that it ends up with an equilibrium that's not optimal. So here's the game. We have two prisoners. We call them player one and player two, and these two prisoners have been captured after a high-speed chase. We believe that they robbed a bank, but we can't prove it. Somehow they got the money out a window on one of the turns when they were driving away. We don't have any videos of them, so all we can really get them on is the high-speed chase. Well, that would be 5 years in prison each, and then they would walk away and be able to keep the money. And so how we handle this is we take each of the prisoners and we put them in separate rooms so they can't talk to each other. And then we make each of them the same offer. If you confess and your partner denies, you're only going to get 4 years in prison and he's going to get 25 years. On the other hand, if he confesses and you deny, he's going to get 4 years in prison. You're going to get 25 years in prison. If you both confess, you'll each get 10 years. However, if you both deny, you'll each get 5 years. Now, it looks like they ought to just both deny and everything would be great. But here's where it gets tricky. This is a game that has what we call a dominant strategy. It's dominant because there's always the same strategy, no matter what the other player does. Let's suppose that player two decides to confess. Well, that would mean, based on the payoffs, that player one, whose payoffs are the first number, would either get 10 years for confessing or 25 years for denying. Now, obviously, he was going to want to pick the 10 years, so he would confess as well. On the other hand, if player two decides to deny, then player one can either get 4 years in prison by confessing or 5 years in prison for denying. Again, he's better off confessing. In both cases, he's better off confessing. This is, again, a dominant strategy. Now, let's look at player two. If player one confesses, player two can either get 10 years in prison by confessing or 25 years for denying. Remember, his payoffs are the second number. Well, obviously, he wants to confess because he only gets 10 years. On the other hand, if player one denies, player two can get 4 years in prison for confessing or 5 years in prison for denying. So again, he's better off confessing. So they're both better off confessing in every single play. And that results in 2 confessions, 10 and 10 years in prison each. Now, how do we solve this game the way I just described it? Well, there's a simple technique. You start by saying if player two chooses to confess, then player one can either get 10 years in prison or 25, and you mark 10 by underscoring it. You then say if player two chooses to deny, then player one can either get -4 or -5, and you underscore the 4. Then you do the same thing for player two and player one. If player one chooses to confess, player two can get either 25 or 10. He's going to want the 10. And if player one chooses to deny, player two is better off choosing the 4. Now, once you've marked it this way, you look at the 4 quadrants and you see if any of them have both numbers underlined. If they're both underlined, that is the equilibrium. And we call this a pure strategy, Nash equilibrium, or a PSNE. And we would mark that box with PSNE. So we have solved the game. Now, obviously not the optimal decision, because they could have both chosen to deny, and then they would have received only 5 years in prison. But that's why it's called the prisoner's dilemma. Now, what I want to do next is I'm going to show you a different way of solving this problem. Now, this game is called the extensive form, and I'm going to show you the extensive form of the prisoner's dilemma. In this game, we create a tree, and in this tree, we have player one in the first position with confess or deny, and then we have player two in the second position, confess and deny, depending on which choice player one makes. And at the end, we have the payoffs. So the first payoff at the top there, -10, -10, represents confess, confess. And if we look in the left-hand corner, we'll see confess, confess from the game we just were playing is -10, -10. Now I could take the normal forms payoffs and transfer them over to this extensive form. Once I've done that, then I take a look at each part of this extensive form as if each one of them is what's called a subgame. And so the first one is subgame number one. Subgame number one is player two's choice. And player two has a choice of the second score, -10 or -25. Well, obviously, he wants -10. And so the score that goes with -10 for player one is -10. So he chooses the -10, and we put the -10 for player one over here. We've now solved subgame one. Now we solve subgame two. Here, the payoffs for player two are the -4 and the -5. I have placed those scores here. And as you can see, he's better off choosing -4. And the score that goes with the -4, the -25 then, transfers here. Now, player one is going to play. And player one is going to play subgame three. In this subgame three, player one's choice is -10 or -25. Of course, he's going to pick the -10, and that means he's going to receive -10 and -10 also for player two. And again, we got the same result. And this is called the extensive form. And what we did was we solved it using reverse induction. Now, reverse induction is going to be a very important tool for us in game theory. And this was, for example, how we would solve the pirate problem that I gave you at the beginning of the semester. So I have uploaded a homework sheet for you. It has 4 games. One of them is this game, and there are 3 others. And what I want you to do is to solve them. And that means first solve the normal form, marking it the way I showed you. Then take the payoffs from that, move them over to the extensive form, and then using reverse induction, solve again to find the payoffs here, and then mark the pathway with a pen so I know that you figured out which way it's going to end up. And that's your homework assignment. It's worth 2 points. Each one of these is worth a half a point. So it's a very easy problem to do, but it will get you a chance to be more familiar with this process.